Hello YouTube, my name is Neil and we're studying for the MCATs today. We're in the Biochemistry review, Chapter 2, Enzymes. There is an obesity epidemic in the United States that is paralleled by an increase in high blood pressure or hypertension. This is extremely relevant to medical students because hypertension increases the risk of stroke, heart failure, and kidney failure. Each year, physicians encourage millions of Americans to improve their diets, add exercise to their daily regimens, or even take prescription drugs to control their hypertension. Many of these anti-hypertensive medications are called ACE, angiotensin-converting enzyme inhibitors. In healthy patients, ACE catalyzes a reaction that converts a peptide called angiotensin 1 to angiotensin 2. The angiotensin 2 peptide then not only directly causes constriction of the blood vessels to raise blood pressure, but also stimulates the release of the hormone aldosterone, which activates the kidneys to reabsorb more water back into the bloodstream. The increase in blood volume also increases blood pressure. Physicians take advantage of this complicated pathway with a straightforward solution. Stop the pathway early by inhibiting ACE, and blood pressure will decrease. We should write this down, because that sounds pretty relevant. Angiotensin converting enzyme is ACE. It's what converts angiotensin 1 into 2, which increases blood pressure. And the ACE inhibitor stops that. Enzymes are crucial proteins that dramatically increase the rate of biological reactions. They're used to regulate homeostatic mechanisms in every organ system and are highly regulated themselves by environmental conditions, activators, and inhibitors. These regulators may be naturally occurring or may be given as a drug, such as the ACE inhibitors used to treat hypertension. Some enzymes are kept in an inactivated form called a zymogen and are only activated as needed. Let's write down Zymogen, which is an inactive enzyme. In this chapter, we'll learn about how enzymes work and how different conditions influence their activity. We'll also see how enzymes are regulated, which will help us tie together concepts about every organ system and metabolic process we learn about for the MCAT. Enzymes as biological catalysts. Enzymes are incredibly important as biological catalysts. Catalysts do not impact the thermodynamics of a biological reaction. That is, the delta H of the reaction and equilibrium position do not change. Instead, they help the reaction proceed at a much faster rate. As a catalyst, the enzyme is not changed during the course of the reaction. Enzymes increase the reaction rate of a process by a factor of 100, 1,000, or even, this is a large number, it's a million, billion, trillion, 1 trillion times when compared to the uncatalyzed reaction. Without this increase, we wouldn't be alive. Table 2.1 summarizes the key points to remember about enzymes. Lower the activation energy. Increase the rate of the reaction. Do not alter the equilibrium constant. Are not changed or consumed in the reaction. Are pH and temperature sensitive. With optimal activity at specific pH ranges and temperatures, they do not affect the overall delta G of the reaction. They are specific for a particular reaction or class of reactions. Do not affect delta G. Enzyme classifications. Enzymes are picky. The molecules upon which an enzyme acts are called substrates. A given enzyme will only catalyze a single reaction or class of reactions with these substrates, a property known as enzyme specificity. For example, urease only catalyzes the breakdown of urea. Chymotrypsin, on the other hand, can cleave peptide bonds around the amino acids phenylalanine, tryptophan, and tyrosine in a variety of polypeptides. Although those amino acids aren't identical, they all contain an aromatic ring, which makes chymotrypsin specific for a class of molecules. Enzymes can be classified into 6 categories based on their function or mechanism. We'll review each type of enzyme and give examples of those that you are most likely to see on test day. If you encounter an unfamiliar enzyme on the MCAT, keep in mind that most enzymes have descriptive names ending in the suffix -ase. Lactase, for example, breaks down lactose. Great. Enzyme specificity, urease, chymotrypsin. We learn about chymotrypsin, but let's write all these down anyways. Urease, just as examples. Urease, chymotrypsin, and lactose. Oxidoreductases. Oxidoreductases. Oxidoreductases catalyze oxidation reduction reactions. That is the transfer of electrons between biological molecules. They often have a cofactor that acts as an electron carrier, such as NAD+ or NADP+. In reactions catalyzed by oxidoreductases, the electron donor is known as the reductant, and the electron acceptor is known as the oxidant. Enzymes with dehydrogenase or reductase in their names are usually oxidoreductases. Enzymes in which oxygen is the final electron acceptor often include oxidase in their names. So let's write down NAD+, NADP+. The electron donor is the reductant, and the electron acceptor is the oxidant. Dehydrogenase or reductase are in this class. All right. Transferases. Transferases catalyze the movement of a functional group from one molecule to another. For example, in protein metabolism, an aminotransferase can convert aspartate and alpha-ketoglutarate as a pair to glutamate and oxaloacetate by moving the amino group from aspartate to alpha-ketoglutarate. Most transferases will be straightforwardly named, but remember that kinases are also a member of this class. Kinases catalyze the transfer of a phosphate group generally from ATP to another molecule. So let's just write down aminotransferase as an example. And kinases specifically transfer a phosphate, which is PO4. Like from ATP. Hydrolases. Hydrolases catalyze the breaking of a compound into two molecules using the addition of water. In common usage, many hydrolases are named only for their substrate. For example, one of the most common hydrolases you will encounter on the MCAT is a phosphatase, which cleaves a phosphate group from another molecule. Other hydrolases include peptidases, nucleases, and lipases, which break down proteins, nucleic acids, and lipids, respectively. Hydrolases, just some examples. Phosphatase, peptidases, nucleases, and lipases. Lyases, L-Y-A-S-E-S, lyases. Lyases catalyze the cleavage of a single molecule into two products. They do not require water as a substrate and do not act as oxidoreductases. Because most enzymes can only catalyze the reverse of their specific reactions, the synthesis of two molecules into a single molecule may also be catalyzed by a lyase. When fulfilling this function, it is common for them to be referred to as synthases. So let's just put synthases in parentheses. Not much to be said there. Isomerases catalyze the rearrangement of bonds within a molecule. Some isomerases can also be classified as oxidoreductases, transferases, or lyases, depending on the mechanism of the enzyme. Keep in mind that isomerases catalyze reactions between stereoisomers as well as constitutional isomers. Isomerases, both stereo and constitutional isomers. Ligases. Ligases catalyze addition or synthesis reactions, generally between large similar molecules, and often require ATP. Synthesis reactions with smaller molecules are generally accomplished by lyases. Ligases are most likely to be encountered in nucleic acid synthesis and repair on test day. So while lyases can do the job, ligases are going to be in DNA for our purposes. Require ATP. Ligase, addition or synthesis, require ATP. DNA. Let's write down that lyases don't require. Let's write down a little bit more information. Let's write that they don't require water. It says that they don't require H2O. It doesn't say ATP. They might use ATP. It doesn't specifically say that they don't, but it implies that it doesn't use anything else, right? Hydrolases use H2O. Transferases, oxidoreductases. Hydrolases also break down. So this is like catabolic. These are both catabolic This can be catabolic and anabolic. All right. Impact on activation energy. Recall that thermodynamics relates the relative energy states of a reaction in terms of its products and reactants. An endergonic reaction is one that requires energy input. Delta G is greater than 0, whereas an exergonic reaction is one in which energy is given off. Delta G is less than 0. Remember that endo means in and exo means out. So endergonic reactions take in energy as they proceed, whereas exergonic reactions release energy as they proceed. We can look at the reaction diagram in figure 2.1 to see this demonstrated more clearly. And this is an exergonic reaction. And we have a lower energy after the reaction than before. And I guess we have what the enzyme, the catalyst does, lowers the activation energy without changing the initial or final delta G's, or initial or final G's. All right, the reaction shown in figure 2.1 is spontaneous. Note that the delta G for this reaction is negative. A very important characteristic of enzymes is that they do not alter the overall free energy change for a reaction, nor do they change the equilibrium of a reaction. Rather, they affect the rate or kinetics at which a reaction occurs. Thus, they can affect how quickly a reaction gets to equilibrium, but not the actual equilibrium state itself. For example, a reaction could take years to approach equilibrium without an enzyme. In comparison with the enzyme, equilibrium might be attained within seconds. Enzymes ensure that many important reactions can occur in a reasonable amount of time in biological systems. Recall that enzymes as catalysts are unchanged by the reaction. What is the functional consequence of this? Far fewer copies of the enzyme are required relative to the overall amount of substrate, because one enzyme can act on many, many molecules of substrate over time. Catalysts exert their effect by lowering activation energy of a reaction. In other words, they make it easier for the substrate to reach the transition state. Imagine having to walk to the other side of a tall hill. The only way to get there is to climb to the top of the hill and then walk down the other side. But wouldn't it be easier if the top of the hill was cut off so one wouldn't have to climb so high? That's exactly what catalysts do for chemical reactions when they make it easier for substrates to achieve their transition state. Most reactions catalyzed by enzymes are technically reversible, although that reversal may be extremely energetically unfavorable and therefore essentially non-existent. How do enzymes function as biological catalysts? How? By lowering the activation energy of reactions, by changing the reaction rate. 2, what is enzyme specificity? Enzyme specificity is that some enzymes are targeting certain compounds. We learned that chymotrypsin targets amino acids with a ring structure. What are the names and many main functions of the 6 different classes of enzymes? The names, not off the top of my head, but from what I wrote down here, are oxidoreductases, transferases, hydrolases, lysases, isomerases, and ligases. Lysase, ligase, isomerase, hydrolase, transferase, oxidoreductase. Functions. The oxidoreductase facilitates oxidation reduction reactions. The transferase will transfer a functional group between 2 chemical compounds. A hydrolase will break down a molecule using water. Oh, wait. Yeah. A lysase will break down a molecule, a compound, but does not require water. It can also be used to anabolically to build compounds. Isomerases will convert between either stereo or constitutional isomers. And ligases will perform either addition or synthesis reactions, usually on DNA, and usually requiring ATP. In what ways do enzymes affect the thermodynamics versus the kinetics of a reaction? It doesn't affect the thermodynamics, it affects the kinetics, right? How long it takes for the reaction, not necessarily where equilibrium is. So is that thermodynamics or is that kinetics? I forget. I'm going to go with thermodynamics. Let's see what they say. 2.1. Catalysts are characterized by two main properties. They reduce the activation energy and they lower its activation energy. They're also regenerated at the end in their original form. Enzyme specificity refers to the idea that a given enzyme will only catalyze a given reaction or type of reaction. For example, serine, threonine specific protein kinases will only place a phosphate group onto the hydroxyl group of a serine or threonine residue. Ligases perform addition or synthesis reactions generally between large molecules, often require ATP. Isomerases rearrange the bonds within a compound. Lyase cleaves a molecule into two products, or synthesis of small organic molecules. Hydrolase, breaking of a compound into two molecules using the addition of water. Oxidoreductase, oxidation reduction reaction, specifically transferring of electrons, in other words. And a transferase, movement of a functional group from one molecule to another. 4. Enzymes have no effect on the overall thermodynamics of the reaction. They have no effect on the delta G or delta H of the reaction, although they do lower the energy of the transition state, thus lowering the activation energy. However, enzymes have a profound effect on the kinetics of a reaction. By lowering activation energy, equilibrium can be achieved faster, although the equilibrium position does not change. What did I say? Did I say thermodynamics for... In what ways do enzymes affect the thermodynamics versus the kinetics of a reaction? They affect not the thermodynamics, not delta G, but the kinetics, the rate at which a reaction happens. Great. 2.2, mechanisms of enzyme activity. All right. Mechanisms. While enzyme mechanisms will vary depending on the reaction that is being catalyzed, they tend to share some common features. Enzymes may act to provide a favorable microenvironment in terms of charge or pH, stabilize the transition state, or bring reactive groups nearer to one another in the active site. The formation of the enzyme substrate complex in the active site of an enzyme is the key catalytic activity of the enzyme, which reduces the activation energy of the reaction as described above. This interaction between a substrate and the active site of an enzyme also accounts for the selectivity and some regulatory mechanisms of enzymes. Enzyme-substrate binding. The molecule upon which an enzyme acts is known as its substrate. The physical interaction between these two is referred to as the enzyme-substrate complex. The active site is the location within the enzyme where the substrate is held during the chemical reaction. Let's write down enzyme substrate complex, active site, the active site assumes a defined spatial arrangement in the enzyme substrate complex, which dictates the specificity of that enzyme for a molecule or group of molecules. Hydrogen bonding, ionic interactions, and transient covalent bonds within the active site all stabilize this spatial arrangement and contribute to the efficiency of the enzyme. Two competing theories explain how enzymes and substrates interact, but one of the two is better supported than the other. Lock and key theory. Lock and key. The lock and key theory is aptly named. It suggests that the enzyme's active site, the lock, is already in the appropriate conformation for the substrate, the key, to bind. As shown in figure 2.3, the substrate can then easily fit into the active site, like a key into a lock or a hand into a glove. No alteration of the tertiary or quaternary structure is necessary upon binding of the substrate. No alteration to tertiary or quaternary structure. So no conformational changes? Induced Fit Model. The more scientifically accepted theory is the Induced Fit Model. This is the one you are more likely to see referenced on test day. Imagine that the enzyme is a foam stress ball and the substrate is a frustrated MCAT student's hand. What's the desired interaction? The student wants to release some stress and relax. As his hand squeezes the ball, both change conformation. The ball is no longer spherical and his hand is no longer flat because they adjust to fit each other well. In this case, the substrate, the student, has induced a change in the shape of the enzyme, the stress ball. This interaction requires energy and therefore this part of the reaction is endergonic. Once the student lets go of the stress ball, we have our desired product, a relaxed, more confident test taker. Letting go of the stress ball is pretty easy and doesn't require extra energy, so this part of the reaction is exergonic. Just like enzymes, foam stress balls return to their original shape once their crushers or substrates let go of them. On a molecular level, demonstrated in figure 2.3, the induced fit model starts with a substrate and an enzyme active site that don't seem to fit together. However, once the substrate is present and ready to interact with the active site, the molecules find that the induced form or transition state is more comfortable for both of them. Thus, the shape of the active site becomes truly complementary only after the substrate begins binding to the enzyme. Similarly, a substrate of the wrong type will not cause the appropriate conformational shift in the enzyme, thus the active site will not be adequately exposed. The transition state is not preferred and no reaction occurs. All right, in the induced fit model, the ligand or the substrate is ligand the same thing as substrate? What does ligand mean? No, they're calling a ligand something else. It is an ion or molecule that binds to a central metal atom to form a coordination complex. In biochemistry, a ligand is a substance that forms a complex with a biomolecule to serve a biological purpose, whatever. Substrate induces conformational changes in the enzyme. Substrate changes conformation of enzyme. Cofactors and coenzymes. Many enzymes require non-protein molecules called cofactors or coenzymes to be effective. These cofactors and coenzymes tend to be small in size, so they can bind to the active site of the enzyme and participate in the catalysis of the reaction, usually by carrying charge through ionization, protonation, or deprotonation. Cofactors and coenzymes are usually kept at low concentrations in cells, so they can be recruited only when needed. Enzymes without their cofactors are called apoenzymes, whereas those containing them are holoenzymes. Cofactors are attached in a variety of ways, ranging from weak non-covalent interactions to strong covalent ones. Tightly bound cofactors or coenzymes that are necessary for enzyme function are known as prosthetic groups. Cofactors and coenzymes. Are they the same thing? They didn't make a distinction between the two. Cofactors / coenzymes. You have the apoenzyme, which has no cofactor, and then the holoenzyme with cofactor. Cofactors and coenzymes are topics that we are likely to see on test day, so they are important to know. Cofactors are generally inorganic molecules or metal ions and are often ingested as dietary minerals. Coenzymes are small organic compounds. Okay, so now they're distinguishing them. Cofactors are going to be your metal ions. Whereas your coenzymes are small organic groups, the vast majority of which are vitamins or derivatives of vitamins such as NAD+, FAD, and coenzyme A. The water-soluble vitamins include the B-complex vitamins and ascorbic acid, which is vitamin C, and are important coenzymes that must be replenished regularly because they are easily excreted. The fat-soluble vitamins A, D, E, and K are better regulated by partitioning coefficients, which quantify the ability of a molecule to dissolve in a polar versus nonpolar environment. Enzymatic reactions are not restricted to a single cofactor or coenzyme. For example, metabolic reactions often require magnesium, NAD+, derived from vitamin B3, and biotin, which is vitamin B7, simultaneously. The MCAT is unlikely to expect memorization of the B vitamins, however, a familiarity with their names may make biochemistry passages easier on test day. And we have a list here. B1 is thiamine, B2 is riboflavin, B3 is niacin, B5 is pantothenic acid, B6 is pyridoxal phosphate, B7 is biotin, B9 is folic acid, and B12 is cyanocobalamin. Cyanocobalamin, great. Coenzymes are often vitamins or derived from vitamins like NAD, FAD, and coenzyme A. The fat-soluble vitamins A, D, E, and K. And partition coefficients quantify the ability of a molecule to dissolve in a polar versus nonpolar environment. Let's just write down that fat soluble ones are A, D, E, and K. And let's also write B1, B2, B3, and B5, B6, B7, B9, and B12, I guess, are the important ones. Thiamine, riboflavin, niacin, pantothenic acid, pyridoxal phosphate, pyridoxal phosphate. B7 is biotin. B9 is folic acid. And B12 is cyanocobalamin. How do the lock and key theory and induced fit model differ? In the lock and key theory, the substrate and the enzyme already fit. No conformational changes in the enzyme is required. In the induced fit model, the enzyme, or the substrate, I guess, actually induces a conformational change in the enzyme. What do cofactors and coenzymes do? How do they differ? I guess just cofactors are even smaller. They're maybe even individual ions, whereas coenzymes are vitamins, which are somewhat complex, molecules that need to be built up from amino acids, I guess. Let's see what they say. 2.2. Lock and key, active site of enzyme fixed exactly around substrate, no alterations to tertiary or quaternary structure, less accurate. I forgot to point that out, that the lock and key is probably not, less evidence for that than the induced fit, in which the active site of enzyme molds itself around substrate only when substrate is present. Tertiary quaternary structure is modified for enzyme to function, and it is the more accurate model. Number 2, cofactors and coenzymes both act as activators of enzymes. Cofactors tend to be inorganic minerals, while coenzymes tend to be small organic compounds, vitamins. In both cases, these regulators induce a conformational change in the enzyme that promotes its activity. Tightly bound cofactors or coenzymes that are necessary for enzyme function are termed prosthetic groups. All right. Enzyme kinetics. All right. Enzyme kinetics. Kinetics of monomeric enzymes. Monomeric. Enzyme kinetics is a high-yield topic that can score us several points on test day. Just as the relief our student derives from squeezing a stress ball depends on a number of factors, such as size and shape of the ball and his or her baseline level of stress, enzyme kinetics are dependent on factors like environmental conditions and concentrations of substrate and enzyme. The concentrations of the substrate, S, and enzyme, E, greatly affect how quickly a reaction occurs. Let's say that we have 100 stress balls and only 10 students to derive stress relief from. This represents a high enzyme concentration relative to substrate. Because there are many active sites available, we will quickly form products, students letting go and feeling relaxed. In a chemical sense, we would reach equilibrium quickly. As we slowly add more substrate, the rate of the reaction will increase. That is, more people will relax in the same amount of time because we have plenty of available stress balls for them to squeeze. However, as we add more and more people and start approaching 100 students, we begin to level off and reach a maximal rate of relaxation. There are fewer and fewer available stress balls until finally all active sites are occupied. Unlike before, inviting more students into the room will not change the rate of the reaction. It cannot go any faster once it has reached saturation. At this rate, the enzyme is working at maximum velocity, denoted by Vmax. The only way to increase Vmax is by increasing the enzyme concentration. In the cell, this can be accomplished by inducing the expression of the gene encoding the enzyme. These concepts are represented graphically in figure 2.4. Michaelis Menten plot of enzyme kinetics. As the amount of substrate increases, the enzyme is able to increase its rate of reaction until it reaches a maximum enzymatic reaction rate, Vmax. Once Vmax is reached, adding more substrate will not increase the rate of reaction. And the K sub M is the concentration of the substrate at which 1/2 of Vmax is achieved. Great. Michaelis-Menten equation. For most enzymes, the Michaelis-Menten equation describes how the rate of the reaction, V, depends on the concentration of both the enzyme E and the substrate S, which forms product P. Enzyme substrate complexes form at a rate K sub 1. The ES complex can either dissociate at a rate of K sub minus 1 or turn into E plus A, or E plus P at a rate K sub cat for catalyst. The rate constant for the catalyst. E plus S equals ES, which equals E plus P. Note that in either case, the enzyme is again available. On test day, the concentration of enzyme will be kept constant. Under these conditions, we can relate the velocity of the enzyme to substrate concentration using the Michaelis-Menten equation. V equals Vmax of the substrate, the concentration of the substrate, over K sub M plus the concentration of the substrate. Let's write some of this down. In fact, let's draw a little rate plot, enzyme kinematic plot, Michaelis-Menten plot. We have Vmax. And we'll do the same thing they do. We have V max and 1/2 V max and K sub M. And, I'm going to skip equation 2.1. We're just going to go straight to equation 2.2. We're going to get that the velocity of the enzyme to substrate. We can relate the velocity of the enzyme to substrate concentration. So this is the velocity of the enzyme is the V max times the substrate concentration over K sub M plus the substrate concentration. All right. Some important and test day relevant math can be derived from this equation. When the reaction rate is equal to half of V max, K sub M equals the concentration of S. When Is that right? How is that? Let's see what they say. V max divided, so we divide each side by 2, or just the left, 1/2 the rate. When the reaction rate is equal to half of V max, why do they call it velocity then if it's reaction rate? Because there's a difference between velocity and reaction rate. Maybe not, we'll see. So you divide V max by 2, 1/2, and then you take the 2 to the other side. You do some algebra. You take the Km plus S over here. Then you take you divide both sides by V max to get Km plus S equals 2S. Divide by 2 and you just get, or not divide by 2, subtract the S and you get Km equals S. Great. At 1/2 of V max, Km, the concentration of substrate is Km. Great. Km can therefore be understood to be the substrate concentration at which half of the enzyme's active sites are full. Km is the Michaelis Constant and is often used to compare enzymes. Under certain conditions, K sub M is a measure of the affinity of the enzyme for its substrate. When comparing two enzymes, the one with the higher K sub M has a lower affinity for its substrate because it requires a higher substrate concentration to be half saturated. Km value is an intrinsic property of the enzyme substrate system and cannot be altered by changing the concentration of substrate or enzyme. Michaelis constant K sub M, affinity of the enzyme for its substrate. And higher K sub M means lower affinity. Higher K sub M, lower affinity, lower K sub M, higher affinity. For a given concentration of enzyme, the Michaelis-Menten relationship generally graphs as a hyperbola, as seen in the Michaelis-Menten plot in figure 2.4. When substrate concentration is less than K sub m, changes in substrate concentration will greatly affect the reaction rate. At high substrate concentrations exceeding K sub m, the reaction rate increases much more slowly as it approaches Vmax, where it becomes independent of substrate concentration. The variable Vmax represents maximum enzyme velocity and is measured in moles of enzyme per second. Also, Vmax can be mathematically related to K, the K constant of the catalyst, which has units of S to the minus 1 per seconds. So Vmax equals the concentration of enzyme times Kcat. Qualitatively speaking, Kcat measures the number of substrate molecules turned over or converted to product per enzyme molecule per second. Most enzymes have Kcat values between 101 and 103. Michaelis-Menten equation above can be restated using Kcat, where V equals Kcat times the concentration of enzyme times the concentration of substrate over K sub m plus the concentration of substrate. At very low substrate concentrations, where K sub m is much greater than the concentration of substrate, this derived equation can be further simplified as V equals Kcat over K sub m times concentration of enzyme times the concentration of substrate. The ratio of Kcat over Km is referred to as the catalytic efficiency of the enzyme. A large Kcat, high turnover, or a small Km, high substrate affinity, will result in a higher catalytic efficiency, which indicates a more efficient enzyme. So Vmax equals concentration of the enzyme times Kcat. And what was Kcat? It is like the second part of our kind of two-step reaction. Does not depend on K1, only Kcat. So I guess that must be the slow part of the equation, huh? Or the reaction. We have, qualitatively speaking, Kcat measures the number of substrate molecules turned over or converted to product. And let's restate the Michaelis equation, Michaelis-Menten. V equals Kcat, concentration of E, concentration of S, all over K sub m. At very low substrate concentrations, where K sub m is much greater than the concentration of S, this derived equation can be further simplified. So I just wrote down the further simplified version. The less simplified version is V equals Kcat, concentration of E, concentration of S, all over K sub m plus the concentration of S. But if this is much greater than this, and we don't really care about it, I guess. And what do we write for small s? For small concentrations of substrate, we further simplify. The ratio of kcat over K sub m is the catalytic efficiency So Km we kind of talked about as a measure of affinity. Kcat is just the rate constant. The rate of this second step. That's why they show us this little diagram of the two steps of the reaction. To understand what the kcat part is, the unloading part, the second half of it. But qualitatively speaking, it's the number of substrate molecules turned over or converted. Let's write it down here that high kcat, high efficiency, low kcat, low efficiency. Of course, it's not just kcat, it's the ratio of kcat to km. Linear Weaver-Burke plots. Lineweaver-Burke. The Lineweaver-Burke plot is a double reciprocal graph of the Michaelis-Menten equation. The same data graphed in this way yield a straight line as shown in figure 2.5. The actual data are represented by the portion of the graph to the right of the y-axis, but the line is extrapolated into the upper left quadrant to determine its intercept with the x-axis. The intercept of the line with the x-axis gives the value of minus 1 over k sub m. The intercept of the line with the y-axis gives the value of 1 over V max. The Lineweaver-Burke plot is especially useful when determining the type of inhibition that an enzyme is experiencing because V max and K sub m can be compared without estimation. Lineweaver-Burke. So here we have two quadrants. We have a purple line, which I'm just going to draw red here. We have our 1 over V max. And 1 over negative K sub m. And so on this graph, what's plotted here is 1 over S and 1 over V. Per seconds per micromole. Interesting. On that other graph, I should put some labels too, huh? Substrate concentration and velocity. All right, cooperativity. Certain enzymes do not show the normal hyperbola when graphed on a Michaelis-Menten plot, V versus S, but rather show sigmoidal S-shaped kinetics owing to cooperativity among substrate binding sites. As shown in figure 2.6, cooperative enzymes have multiple subunits and multiple active sites. Subunits and enzymes may exist in one of two states, a low affinity tense state or a high affinity relaxed state. Binding of the substrate encourages the transition of other subunits from the T state to the R state, which increases the likelihood of substrate binding by these other subunits. Conversely, loss of substrate can encourage the transition from the R state to the T state and promote dissociation of substrate from the remaining subunit. Think of cooperative enzyme kinetics like a party. As more people start arriving, the atmosphere becomes more relaxed and the party seems more appealing. But as people start going home, the party dies down and more people are encouraged to leave so the tense hosts can clean up. Enzymes showing cooperative kinetics are often regulatory enzymes and pathways like phosphofructokinase 1 in glycolysis. Cooperative enzymes are also subject to activation and inhibition, both competitively and through allosteric sites. Cooperativity can also be quantified using a numerical value called Hill's coefficient. The value of Hill's coefficient indicates the nature of binding by the molecule. If Hill's coefficient is greater than 1, positive cooperative binding is occurring, such that after one ligand is bound, the affinity of the enzyme for further ligands increases. If Hill's coefficient is less than 1, negatively cooperative binding is occurring, such that after one ligand is bound, the affinity of the enzyme for further ligands decreases. If Hill's coefficient equals 1, the enzyme does not exhibit cooperative binding. Cooperativity. S-shaped curve. That wasn't good. Let's do that again. Whatever. R is relaxed, T is tense, R is relaxed. Some examples: phosphofructokinase, one in glycolysis, and are they actually going to talk about competitive inhibition and allosteric reverse inhibition irreversible inhibition, uncompetitive inhibition, mixed inhibition, non-competitive, competitive. All right, we'll get into all of that. Cooperativity is measured with Hill's coefficient. Greater than 1 and less than 1 or equal to 1. Greater than 1, less than 1, equal to 1. Positive cooperative binding probably isn't even necessary. I still will write greater than or less than 1. Greater than 1. Positive. That sounds silly to say, but positive. Less than 1. Negative. Cooperativity. What are the effects of increasing the concentration of S on enzyme kinetics? What about increasing the concentration of E? Well, according to this, increasing S does not really help. Well, I guess it does. It's times S up here and plus S up here. So it has a greater effect on top. So increasing S increases V, increasing E increases V. Here you go, E and S, increasing both will increase the rate. 2, how are the Michaelis-Menten and Lineweaver-Burke plots similar, and how are they different? Similarities. They both give you K sub m and Vmax values. The difference is that as this is hyperbolic, it can be difficult to estimate where 1/2 Vmax and Vmax are. On the linear version, Vmax and K sub m are a little bit more obvious. Easier to estimate. What does K sub m represent, and what would an increase in K sub m signify? We learned that K sub m is a measure of affinity, where low K sub m is high affinity. So increasing K sub m would decrease affinity. What do the x and y intercepts in the Lineweaver-Burke plot represent? The x represents 1 over the concentration of S, and the x-intercept. That's the x-axis. The x-intercept represents 1 over K sub m, minus 1 over K sub m rather, and the y-intercept represents 1 over Vmax. What is enzyme cooperativity? When like multiple subunits in a protein in an enzyme, after one subunit is filled, like the binding site is filled with the ligand, the other subunits will have a conformational change that increases their affinity. And so the rate of the enzyme can be enhanced. Similarly, when they start leaving, the enzyme also goes through conformational changes in which the leaving of the first ligand facilitates the leaving of the second, facilitates the leaving of the third. I think that's the case for hemoglobin. Do they say hemoglobin? They don't say what enzyme does this, but I'm pretty sure hemoglobin does this. All right. Hemoglobin has 4 subunits that can each hold an oxygen, an O2 or an O. I'm not really sure if it's an O2 or a single oxygen. It's got to be an O2, right? How many oxygens does hemoglobin hold? Four oxygen molecules. So that's not oxygen atoms. Oxygen molecules have to be O2, right? If it was oxygen atoms, here's another question. How many oxygen atoms? Yeah, it's 8. 8 atoms, 4 molecules. Great. If we check the answers to these, I'm pretty confident about those. No, we should see what they say. Let's see what they say. 2.3. 1. Increasing the concentration of S of the substrate has different effects depending on how much substrate is present to begin with. When the substrate concentration is low, an increase in S causes a proportional increase in enzyme activity. At high S, however, when the enzyme is saturated, increasing S has no effect on activity because Vmax has already been attained. Increasing E will always increase Vmax regardless of the starting concentration of enzyme. Interesting. 2. Both the Michaelis-Menten and Lineweaver-Burke relationships account for the value of Km and Vmax under various conditions. They both provide simple graphical interpretations of these two variables and are derived from the Michaelis-Menten equation. However, the axes of these graphs and visual representation of this information is different between the two. Michaelis-Menten plot is a V versus concentration of S, which creates a hyperbolic curve for monomeric enzymes. The Lineweaver-Burke plot, on the other hand, is 1 over V versus 1 over concentration of S, which creates a straight line. K sub m is a measure of an enzyme's affinity for its substrate and is defined as the substrate concentration at which an enzyme is functioning at half its maximal velocity. As Km increases, an enzyme's affinity for its substrate decreases. The x-intercept, number 4, represents minus 1 over Km. The y-intercept represents 1 over Vmax. 5. Cooperativity refers to the interactions between subunits in a multi-subunit enzyme or protein. The binding of substrate to one subunit includes a change in other subunits from the T tense state to the R relaxed state, which encourages binding of substrate to the other subunits. In the reverse direction, the unbinding of substrate from one subunit induces a change from R to T in the remaining subunits, promoting unbinding of substrate from the remaining subunits. Great. 2.4. Effects of local conditions on enzyme activity. The activity of an enzyme is heavily influenced by its environment, in particular temperature, acidity, or alkalinity, pH, and high salinity have significant effects on the ability of an enzyme to carry out its function. Note that the terms enzyme activity, enzyme velocity, and enzyme rate are all used synonymously on the MCAT. So enzyme activity influenced by temperature, pH, salinity, and also enzyme activity, velocity, and rate are used interchangeably. Equals velocity equals rate. Great. Temperature. Enzyme catalyzed reactions tend to double in velocity for every 10 degrees increase in temperature until the optimum temperature is reached. For the human body, this is 37 degrees Celsius or 98.6 Fahrenheit, as well as 310 Kelvin. After this, activity falls off sharply, as the enzyme will denature at higher temperatures as shown in figure 2.7. Some enzymes that are overheated may regain their function if cooled. A real-life example of temperature dependence occurs in Siamese cats. Siamese cats are dark on their faces, ears, tails, and feet, but white elsewhere. Why? The enzyme responsible for pigmentation, tyrosinase, is mutated in Siamese cats. It is ineffective at body temperature, but at cooler temperatures becomes active. Thus, only the tail, feet, ears, and face, cooled by air passing through the nose and mouth, have an active form of the enzyme and are dark. That is interesting. Temp. (2V) for, let's write 2x. 2 times velocity for every 10 degrees Celsius. pH. Most enzymes also depend on pH in order to function properly, not only because pH affects the ionization of the active site, but also because changes in pH can lead to denaturation of the enzyme. For enzymes that circulate and function in human blood, this optimal pH is 7.4. As shown in figure 2.7, a pH less than 7.35 in human blood is termed acidemia. Even though it's more basic than chemically neutral, 7.0, it is more acidic than physiologically neutral, 7.4. Where might exceptions to this pH of 7.44 occur? Both are in our digestive tract. Pepsin, which works in the stomach, has maximal activity around pH 2, whereas pancreatic enzymes, which work in the small intestine, work best around a pH of 8.5. Small intestines is basic. I did not realize that the small intestine was 8.5. I didn't think it went above 7.4. That's fantastic. Should we put an example of... Let's put an example of tyrosinase. Tyrosinase, pH, physiological pH is physiological pH equals 7.4. Let's write down stomach is around 2. Small intestine is around 8.5. Wow. I guess this one we're talking about pepsin, and these would be pancreatic. All right, salinity. While the effect of salinity or osmolarity is not generally of physiological significance, altering the concentration of salt can change enzyme activity in vitro. Increasing levels of salt can disrupt hydrogen and ionic bonds, causing a partial change in the conformation of the enzyme, and in some cases cause denaturation. Salinity disrupts hydrogen and ionic bonds. Denature enzymes. Number 1, what are the effects of temperature, pH, and salinity on the function of enzymes? Temperature increases the efficiency of an enzyme up to a certain point, then it will denature the enzyme. Similarly, pH, there is a ideal pH for every enzyme, and outside of that range, it just won't work. I don't know about it being denatured quite the same, but salinity will denature enzymes. Number 2, what is the ideal temperatures for most enzymes in the body? The ideal pH. Ideal temperature is going to be 98.6. Let's also write this down, that 98.6 is the same as 37, which is the same as 310 degrees Kelvin. Ideal pH is 7.4 for most enzymes. For gastric enzymes, around 2. Pancreatic enzymes, I guess 8.5. Regulation of enzyme activity. Should we check answers to those? We should. Let's do that real quick. (2.41) as temperature increases, enzyme activity generally increases until it denatures. Enzymes are maximally active within a small pH range, and the protein is denatured by pH. Changes in salinity will denature. Number 2, ideal temperature 37 degrees Celsius, ideal pH 7.4, 2 for gastric and 8.5 for pancreatic. Great. (2.5) Regulation of enzyme activity. Regulation. Although enzymes are useful, the body must be able to control when they work. For example, enzymes involved in mitosis should be shut off when cells are no longer dividing in the G0 phase. This may be accomplished in a variety of ways as described below. Feedback regulation. Enzymes are often subject to regulation by products further down a given metabolic pathway, a process called feedback regulation. Less often, enzymes may be regulated by intermediates that precede the enzyme in the pathway, also called feed-forward regulation. This is clearly evident in the study of metabolism as discussed in chapters 9 through 12 of biochemistry. While there are some examples of feedback activation, feedback inhibition is far more common. Feedback inhibition or negative feedback helps maintain homeostasis once we have enough of a given product. We want to turn off the pathway that creates that product rather than creating more. In feedback inhibition, the product may bind to the active site of an enzyme or multiple enzymes that act earlier in its biosynthetic pathway, thereby competitively inhibiting these enzymes and making them unavailable for use. This is schematically represented in figure 2.8 as we see product D feeding back to inhibit the first enzyme in the pathway. Feedback regulation, negative feedback, and positive feedback. Feed-forward regulation. Feedback, more common. Feedback activation. So feedback inhibition is more common than feedback activation. Feedback inhibition is negative feedback. Positive feedback is not really discussed. Versus feed forward. We have that inhibition, more common than activation. All right. Reversible inhibition. There are 4 types of reversible inhibition: competitive, non-competitive, mixed, and uncompetitive. On test day, you will most often encounter competitive and non-competitive inhibition, but be aware of the differences in the 4 types. Table 2.2 at the end of this section summarizes the features of each type of reversible inhibition. Competitive. Competitive inhibition simply involves occupancy of the active site. Substrates cannot access enzyme binding sites if there is an inhibitor in the way. Competitive inhibition can be overcome by adding more substrate so that the substrate to inhibitor ratio is higher. If more molecules of substrate are available than molecules of inhibitor, then the enzyme will be more likely to bind substrate than inhibitor, assuming the enzyme has equal affinity for both molecules. Adding a competitive inhibitor does not alter the value of Vmax because if enough substrate is added, it will outcompete the inhibitor and be able to run the reaction at maximum velocity. A competitive inhibitor does increase the measured value of Km. This is because the substrate concentration has to be higher to reach half the maximum velocity in the presence of the inhibitor. A Lineweaver-Burke plot comparing an enzyme with and without a competitive inhibitor is shown in figure 2.9. So, in the Lineweaver-Burke plot, our y-intercept is the same, while our x-intercept has changed. K sub m has changed, V max has not. Equal V max increased K sub m as shown in our diagram. I guess I should make a 2-quadrant graph. And we have our gradual no inhibitor line and our steep, let's do that again. Whoops. Our steep inhibitor line. Non-competitive inhibition. Non-competitive inhibitors bind to an allosteric site instead of the active site, which includes a change in enzyme conformation. Allosteric sites are non-catalytic regions of the enzyme that bind regulators. Because the two molecules do not compete for the same site, inhibition is considered non-competitive and cannot be overcome by adding more substrate. Non-competitive inhibitors bind equally well to the enzyme and the enzyme substrate complex, unlike the mixed inhibitors. Once the enzyme's conformation is altered, no amount of extra substrate will be conducive to forming an enzyme substrate complex, unlike mixed inhibitors. Once the enzyme's conformation is altered, no amount of extra substrate will be conducive to forming an enzyme substrate complex. Adding a non-competitive inhibitor decreases the measured value of B max or V max because there is less enzyme available to react. It does not, however, alter the value of K sub m because any copies of the enzyme that are still active maintain the same affinity for their substrate. A Lineweaver-Burke plot of an enzyme with and without a non-competitive inhibitor is shown in figure 210. And here the x-intercept has not changed while the y-intercept has. So we'll write non-competitive. Here, V max decreases the value of V max and does not change K sub m. And our Lineweaver-Burke plot now looks like this. Mixed inhibition. Mixed inhibition results when an inhibitor can bind to either the enzyme or the enzyme substrate complex but has different affinity for each. If the inhibitor had the same affinity for both, it would be a non-competitive inhibitor. Mixed inhibitors do not bind at the active site but at an allosteric site. Mixed inhibitors alter the experimental value of K sub m depending on the preference for the inhibitor for the enzyme versus the enzyme substrate complex. If the inhibitor preferentially binds to the enzyme, it increases the K sub m value, thus lowers its affinity. If the inhibitor binds to the enzyme substrate complex, it lowers K sub m, increasing affinity. In either case, Vmax is decreased. On a Lineweaver-Burke plot, the curves for the activity with and without the inhibitor intersect at a point that is not on either axis. So both K sub n and Vmax is changed. So they don't draw one, but we could theorize. Before I do that, I want to write down one more thing. What an allosteric site is. Allosteric sites are non-catalytic but they do change the conformation of the enzyme, right? Once the enzyme's conformation is altered, no amount of extra substrate will be conducive to forming an enzyme substrate complex. Non-catalytic changes enzyme conformation. Changes enzyme conformation. Mixed inhibition. Can attach to either the allosteric site or the binding site. I take that back. It can bind to either the enzyme alone or the enzyme substrate complex, while the non-competitive inhibitor only binds to the enzyme without the complex. Non-competitive inhibitors bind equally well to the enzyme and the enzyme substrate complex. So I reverse that. Non-competitive inhibitors will bind equally well to enzyme and enzyme substrate complexes, while mixed inhibitors can better bind to one or the other, can bind to either the enzyme or the enzyme substrate complex. It has different affinity to both. They do not bind at the active site, but at an allosteric site. So let's write that non-competitive inhibitors bind to enzyme and enzyme complex equally, while the mixed inhibitor binds to either the enzyme or the enzyme substrate. I think I forgot the word substrate here. Binds to either enzyme or enzyme substrate complex. Preferentially. And even though they didn't write our Lineweaver-Burke plot, I imagine they said that the two lines do not cross on one of the axes. So both Km and Vmax will change. I guess Km goes up, Vmax goes down. All right, uncompetitive inhibition. We did non-competitive. Now we got uncompetitive. Uncompetitive inhibition. Uncompetitive inhibitors bind only to the enzyme substrate complex and essentially lock the substrate in the enzyme, preventing its release. This can be interpreted as increasing affinity between the enzyme and substrate. Because the enzyme substrate complex has already formed upon binding, uncompetitive inhibitors must bind at an allosteric site. In fact, it is the formation of the enzyme substrate complex that creates a conformational change that allows the uncompetitive inhibitor to bind. Thus, uncompetitive inhibitors lower Km and Vmax. On a Lineweaver-Burke plot, the curves for activity with and without an uncompetitive inhibitor are parallel. All right, uncompetitive inhibitors bind to enzyme substrate complex alone. I guess the competitive inhibition is that it binds to enzyme because it binds to the binding site. While the non-competitive inhibitor binds to the allosteric site, mixed inhibitor, and uncompetitive inhibitor all bind to the allosteric site. And let's draw our Lineweaver-Burke plot. They say that this will make two parallel lines. K sub m has decreased and Vmax has they've both decreased. Because remember, this is an inverse graph, so the higher numbers, or the higher on the line, is lower Vmax and K sub m as well. Binding site. Competitive is at the active site. Non-competitive, mixed, and uncompetitive are all at the allosteric sites. Impact on K sub M. Increases, unchanged, increases or decreases, or decreases. So we should make 2 of these, because 2 are possible. I could do that to it. I guess it could also do that to it or something. Okay. Impact on Vmax decreases. Never mind. It cannot do that. So you could have, so it'll only increase Km. You could have it, or it only decreases Vmax. So the y-intercept is going to be higher, but Km could be greater or less than. So let's do that. Those are 2 options. Increases or decreases. So impact on K sub M. Competitive increases K sub N. Non-competitive does not change K sub M. Mixed can increase or decrease K sub M. And the uncompetitive inhibitor decreases K sub M. Impact on Vmax. The competitive inhibitor does not change Vmax. The non-competitive inhibitor decreases Vmax. Mixed inhibitor the mixed inhibitor will decrease Vmax, and the uncompetitive inhibitor will also decrease Vmax. Irreversible inhibition. In this type of inhibition, the active site is made unavailable for a prolonged period of time, or the enzyme is permanently altered. In other words, this type of inhibition is not easily overcome or reversed. A real-world example is aspirin. Acetylsalicylic acid, aspirin, irreversibly modifies cyclooxygenase 1. This enzyme can no longer bind its substrate, arachidonic acid, to make its products, prostaglandins, which are involved in modulating pain and inflammatory responses. To make more prostaglandins, new cyclooxygenase 1 will have to be synthesized through transcription and translation. Irreversible inhibition is a prime drug mechanism, and something that you will come across often in medical school. Irreversible inhibition aspirin, which is acetylsalicylic acid, modifies cyclooxygenase 1 which of course make prostaglandins from arachidonic acid. Arachidonic arachidonic acid to prostaglandins. All right. Regulated enzymes. Allosteric enzymes. Enzymes that are allosteric have multiple binding sites. The active site is present as well as at least one other site that can regulate the availability of the active site. These are known as allosteric sites. Allosteric enzymes alternate between an active and an inactive form. The inactive form cannot carry out its enzymatic reaction. Molecules that bind to the allosteric site may be either allosteric activators or allosteric inhibitors. Binding of either causes a conformational shift in the protein. However, the effect differs. An activator will result in a shift that makes the active site more available for binding to the substrate, whereas an inhibitor will make it less available. In addition to being able to alter the conformation of the protein, binding of activators or inhibitors may alter the activity of the enzyme. As shown in figure 2.6 above, Michaelis-Menten plots of cooperative allosteric enzyme kinetics often have a sigmoidal S-shaped curve. Covalently modified enzymes. In addition to transient interactions, enzymes are often subject to covalent modification. Enzymes can be activated or deactivated by phosphorylation or dephosphorylation. One cannot predict whether phosphorylation or dephosphorylation will activate an enzyme without experimental determination. Glycosylation, the covalent attachment of sugar moieties, is another covalent enzyme modification. Glycosylation can tag an enzyme for transport within the cell, or it can modify protein activity and selectivity. Specific mechanisms for the modification of enzymes by glycosylation are still being studied and are beyond the scope of the MCAT. Let's write some of these down. Allosteric. Activation and inhibition. There's covalently modified enzymes. Covalently modified includes phosphorylation / dephosphorylation, glycosylation, and that'll do. Zymogens. Certain enzymes are particularly dangerous if they are not tightly controlled. These include the digestive enzymes like trypsin, which if released from the pancreas in an uncontrolled manner would digest the organ itself. To avoid this danger, these enzymes and many others are secreted in inactive zymogens like trypsinogen. Zymogens contain a catalytic active domain and regulatory domain. The regulatory domain must be either removed or altered to expose the active site. Apoptotic enzymes like capsases exhibit similar regulation. Most zymogens have the suffix ogen, O-G-E-N. Zymogens like trypsin, so let's write trypsinogen first, because trypsinogen becomes trypsin. And trypsinogen is inactive. Trypsin is active. Another example would be capsases. What is feedback inhibition? Feedback inhibition is negative regulation. Well, I guess it's a regulation that affects a enzyme earlier in the pathway. That's feedback. And inhibition is that it prevents its activity, it decreases its activity rather than increases. What are the 4 types of reversible inhibitors? The 4 types of reversible inhibitors are competitive inhibitors, non-competitive inhibitors, mixed inhibitors, and uncompetitive inhibitors. On the other hand, irreversible inhibitors can damage an enzyme to the point that it's unsalvageable. You just have to synthesize more of the enzyme. What are some examples of transient and covalent enzyme modification? Transient and covalent. I guess transient refers to the allosteric. They never called it transient, but sure, if that's what you want to call it. Transient or are they talking about Zymogens? Yeah, we're going to say transient is allosteric, and we're going to say some examples of allosteric enzymes or modifications. Some allosteric modifications would be like, I'm sure they talked about it. They don't actually give us examples. Covalent would be phosphorylation, glycosylation. But allosteric, they don't even give us examples. They give us trypsinogen and trypsin, that's Zymogens. We got the prostaglandins, that's irreversible. They don't give us any examples of feedback inhibition. Even up here, they're just talking about it in abstracts. I guess we, earlier in the chapter, they told us about, what in the intro, what did they tell us about? Angiotensin and ACE inhibitors. So I guess an example of allosteric would be ACE inhibitors. An example of covalent would be phosphorylation and glycosylation. Why are some enzymes released as Zymogens? Kind of because they're so dangerous on their own. They could, for example, break down your own tissue. And so to keep them in check until you need them, they're released in an inactive form until it's time to use them. Should we see the answers? 2.5, feedback inhibition refers to the product of an enzymatic pathway turning off enzymes further back in that same pathway. This helps maintain homeostasis as product levels rise. The pathway creating that product is appropriately downregulated. The 4 types of inhibitors are competitive, non-competitive, mixed, and uncompetitive. Irreversible inhibition refers to the prolonged or permanent inactivation of an enzyme such that it cannot be easily renatured to gain function. Examples of transient modifications include allosteric activation or inhibition. Examples of covalent modifications include phosphorylation and glycosylation. Zymogens are precursors of active enzymes. It is critical that certain enzymes, like the digestive enzymes of the pancreas, remain inactive until arriving at their target site. Great. Practice questions in a minute after I go to the bathroom. All right. Practice questions. Number 1. Let's move this over a little so we can see everything nice. These pages with the practice questions are a little bit wider, so I gotta condense my field of view a little bit. All right. Number 1, consider a biochemical reaction A to B, which is catalyzed by AB dehydrogenase. Which of the following statements is true? The reaction will proceed until the enzyme concentration decreases. The reaction will be most favorable at 0 degrees Celsius. It's probably not true. A component of the enzyme is transferred from A to B. Dehydrogenase, probably not. The free energy change, delta G, of the catalyzed reaction is the same as for the uncatalyzed reaction. That is true. We know that all enzymes do not change delta G of the product or reactants, only the transition state. So I don't even like that they say that, because it does change delta G for the transition state, for a part of the curve, just not for the beginning or end of the curve. So not the total change, not the delta G, I guess. The instantaneous G at any part of the reaction. So let's go with D. 2. Which of the following statements about enzyme kinetics is false? An increase in the substrate concentration at constant enzyme concentration, increase in the substrate concentration at a constant enzyme concentration leads to proportional increase in the rate of the reaction. Sure. B, most enzymes operating in the human body work best at a temperature of 37 degrees Celsius. Sure, yeah, that's right. An enzyme substrate complex can either form a product or dissociate back into the enzyme and substrate. Yeah, I guess that's also true. Maximal activity of many human enzymes occurs around pH 7.4. Yeah, that's also true. D is true, B is true. An increase in the substrate concentration leads to proportional increase in the rate concentration. That's not proportional because you're also dividing by a piece of the S. Maybe, so I'll say, it's some proportionality. It's not, yeah. C, an enzyme substrate complex can either form a product or dissociate back into the enzyme and substrate. So the complex, let's look at this reaction again. The complex can dissociate back into the enzyme and substrate, or it could dissociate into an enzyme and a product. It doesn't only make a product. I think this is inaccurate because it says it can either form a product or dissociate back into the enzyme and substrate. It can make it doesn't just make a product. It has to, the enzyme is always replenished at the end, right? So let's go with C. C is the one that is false. Some enzymes require the presence of a non-protein molecule to behave catalytically. An enzyme devoid of this molecule is called a non-protein molecule is like the ion. So it's like a cofactor. So the cofactor, the enzyme without the cofactor, no cofactor is the apoenzyme, while the holoenzyme is with the cofactor. Coenzyme just describes the whole thing. Zymoenzyme, not quite. Zymogen isn't quite that. 3 is that apoenzyme, B. 4. Which of the following factors determine an enzyme's specificity? Three-dimensional shape of the active site, the Michaelis constant, the type of cofactor required for the enzyme to be active, or the prosthetic group on the enzyme. The three-dimensional shape of the active site. The Michaelis constant has to do with affinity, the type of cofactor required, not so much the type of cofactor, but just the fact that it requires a cofactor. The prosthetic group on the enzyme. They might not all have prosthetic groups. We'll go with the three-dimensional shape of the active site. 4A. 5. Enzymes increase the rate of a reaction by decreasing the activation energy, decreasing the overall free energy change of the reaction, increasing the activation energy, or increasing the overall free energy change of the reaction. Decreasing the activation energy. 5A. 6. In the equation below, substrate C is an allosteric inhibitor to enzyme 1. Which of the following is another mechanism necessarily caused by substrate C. Negative feedback. Competitive inhibition, we don't know what kind of inhibition this is. It's an allosteric inhibitor. Oh, so if it's an allosteric, we do kind of know? Because the competitive inhibition is not allosteric. So it's not competitive. I don't think it's irreversible. It's not feedback enhancement. If it's an inhibitor, then it's negative feedback. 6D. The activity of an enzyme is measured at several different substrate concentrations, and the data are shown in the table below. K sub m for this enzyme is approximately V max being 100. 1/2 of that is 50. So K sub m is that concentration, 0.5. 0.5. 7A. 8. Questions 8 and 9 refer to the following statement. Consider a reaction catalyzed by an enzyme A with a K sub m value of 5 times 10 to the negative 6th molar and Vmax of 20 millimoles per minute at a concentration of 5 times 10 to the negative 6th. The rate of the reaction will be K sub m value is 1/2 Vmax. So at that concentration, 1/2 of Vmax would be 10. 8 is A. 9. At a concentration of 5 times 10 to the negative 5th molar, the rate of the reaction will be interesting. So, I made a little graph. Let's do the other one. Let's do this one. This is Vmax. Is 20. And halfway was 10. And that K sub m was 5 times 10 to the minus 6th. So now we're considering 5 times 10 to the minus 4th. 5 times 10 to the minus 6 is 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4. Okay, so we're not just looking at a graph. We're just using we're using these equations up here. It looks like it's for small concentrations, right? But I don't know what the concentrations of enzyme is, so I can't say that it's small. So we're going to use this. Now we're going to use this. V max times the concentration over Km plus the concentration. Let's plug that in and see what happens. Do we have a kcat? We don't. Right, so we're using this. V max, which was 20, times concentration, which is 0.0005 equals 0.01, and then K sub m is 5 times 10 to the minus 6 plus concentration. So we go, you know what, I'm going to grab this equation real quick. V max S over Km plus S. This equals V. Here we have 20 times 0.0005 over 0.000005 plus 0.0005. So 0.000505. And this is 0.01. So let's do that last calculation. This divided by 0.000505. 19. Nearly 20. So let's go with that. Let's do this calculation again on this calculator. 20 times 0.005 is 0.1, not 0.01. 0.1. 20 times 0.005 equal, I messed it up. 0.0005 times 20 is 0.01, and then 0.000005 plus 0.0005 equals 0.000505. 0.01 divided by 0.000505 equals 19.8. Right, 20. It's got to be. 9C. All right. Number 10. The graph below shows kinetic data obtained for flu virus enzyme activity as a function of substrate concentration in the presence and absence of two antiviral drugs. And so we have the no inhibitor, we have with Tamiflu, and with Relenza. Based on the graph, which of the following statements is correct? Both drugs are non-competitive inhibitors of the viral enzyme. Tamiflu increases the K sub m value for the substrate compared to Relenza. So higher numbers is lower, lower numbers is higher. Tamiflu raises the K sub m value. Sounds right. Relenza increases the V max value for the substrate compared to Tamiflu. Relenza's y-intercept is higher, which means that the Vmax is actually lower. So that's not true. Both drugs are competitive inhibitors of the viral enzyme. So let's go back to our inhibitions. Competitive inhibition. Vmax doesn't change, but Km does. Tamiflu could be a competitive inhibitor. But not both drugs. Non-competitive inhibitors decrease Vmax, but leave K sub m the same. Relenza could be a non-competitive inhibitor, but still not both. So, Tamiflu increases the K sub m value for the substrate compared to Relenza. That sounds right. 10 is B. 11. The conversion of ATP to cyclic AMP, an inorganic phosphate, is most likely catalyzed by which class of enzyme? Ligase, hydrolase, lyase, or transferase? ATP is adenosine tryptophosphate. AMP must be adenosine monophosphate. And so we're cutting off phosphates. So it's a phosphatase. Is it? No, it's not a phosphatase. It's a kinase. Transfer of PO4. Oops. It's a transferase. D. 12. Which of the following is not a method by which enzymes decrease the activation energy for biological reactions? By modifying the local charge environment, by forming transient covalent bonds, by acting as electron donors or acceptors, or by breaking bonds in the enzyme irreversibly to provide energy. The enzyme does not change irreversibly. 12 is the one that it doesn't do. D is the one that enzymes don't do, is not a method by which enzymes decrease the activation energy. 13. A certain cooperative enzyme has 4 subunits, 2 of which are bound to substrate. Which of the following statements can be made? The affinity of the enzyme for the substrate has just increased. The affinity for the enzyme for the substrate has just decreased. The affinity... 2 of the 4 subunits are bound. We don't know if they're being bound or being unbound, but A is that the affinity has just increased. B is that the affinity has just decreased. C, the affinity of the enzyme for the substrate is at the average for this enzyme class. D, the affinity of the enzyme for the substrate is greater than with a substrate bound. The affinity for the enzyme for the substrate is greater than with a substrate bound. Yeah, D also we don't know if it's which direction we're going. But for C, it doesn't matter which direction we're going. The affinity of the enzyme for the substrate is at the average for this enzyme class. It's right in the middle. We don't know if it's increasing or decreasing, but we do know that it's in the middle. I'm going to go with C. 14. Which of the following is least likely to be required for a series of metabolic reactions? Triglycerol acting as a coenzyme, oxidoreductase enzymes, magnesium acting as a cofactor, or transferase enzymes. For a series of metabolic reactions. Triglycerol acting as a coenzyme, metabolic doesn't say catabolic or anabolic, but triglycerol is part of metabolism. Oxidoreductase enzymes. What did we learn that oxidoreductase was for? NAD, NADP. Sounds pretty metabolic. Magnesium acting as a cofactor. Transferase enzymes. Kinases. Transferase, oxidoreductase, triglycerol, they all sound good. Magnesium acting as a cofactor. I don't know where that fits in. Do we have examples of cofactors? Of course they give us examples of cofactors, right? Coefficient, coenzyme, cofactors and coenzymes. NAD, FAD, vitamins. Let's see. Fat soluble. I just want to add that these are water soluble. Which one is least likely to be a part of metabolism? Transferases. We know that that's in glycolysis, right? So not D. Magnesium acting as a cofactor. Where is magnesium a cofactor in the body? Magnesium cofactor in DNA polymerase. There you go. Oxido reductase, NAD, NADP, electron transport chain. That is part of metabolism as well, right? Glycolysis, the end of glycolysis, the electron transport chain. Triglycerol acting as a coenzyme. Triglycerides are what your body turns into, a fat that your body turns sugar into. Is it a coenzyme? Synthesis of triglycerol by acyl coenzyme A. Yeah, so we'll go with magnesium being the one that doesn't fit because it's DNA polymerase. It's replication. It's not like glycolysis or something. So yeah, 14 is going to be C. And finally, 15. How does the ideal temperature for a reaction change with and without an enzyme catalyst? The ideal temperature is generally higher with a catalyst than without. The ideal temperature is generally lower with a catalyst. The ideal temperature is characteristic of the reaction, not the enzyme. No conclusion can be made without knowing the enzyme type. I guess we don't know, huh? I would go with I don't know. Let's look at the chapter real quick at the effect on temperature, or the effect of temperature. Is so the CAT enzyme, the Siamese CAT enzyme, is ineffective at body temperature, but at cooler temperatures becomes active. I guess that's rare, but it could go in the opposite direction. The ideal temperature is characteristic of the reaction, not the enzyme. That's the one that sounds right. No. No conclusion can be made without knowing the enzyme type. Because if it's that Siamese CAT enzyme, then it's better at cooler temperatures. But that the ideal temperature is generally higher with a catalyst than without, I don't think that changes temperature, right? No, they said that this catalyst gets activated at low temperatures, this CAT enzyme. So yeah, D. We don't know if we're talking about the CAT enzyme or not. Let's check our answers. Number 1, D. 2 is going to be A, not C. Most enzymes in the body operate at maximal activity around a temperature of 37 and a pH of 7.4, which is the pH of most body fluids. In addition, as characterized by the Michaelis-Menten equation, enzymes form an enzyme-substrate complex, which can either dissociate back into the enzyme and substrate or proceed to form a product. So far, we can eliminate choices B, C, and D, so let's check choice A. An increase in the substrate concentration while maintaining a constant enzyme concentration leads to a proportional increase in the rate of the reaction only initially. However, once most of the active sites are occupied, the reaction rate levels off, regardless of further increase in substrate concentration. At high concentrations of substrate, the reaction rate approaches its maximum velocity and is no longer changed by further increase in substrate concentration. So, for number 2, that they didn't add that when it makes a product, the enzyme is still intact. I guess that's irrelevant. They're not trying to get that detailed with it. They're just trying to say that the reaction, like once it's at the transition state, it can go back to the reactants or proceed to the products. And so taking it at that level, that's fine, that's true. On the other hand, A, an increase in the substrate concentration leads to proportional increase in the rate of the reaction. It's not proportional. In the beginning, it has a greater effect. Later, the effect changes, right? As you're later in the reaction, as you get closer to V max, the relationship of substrate concentration and velocity becomes less and less proportional. It matters less at high concentrations, right? Is that what they're saying? Let's read that last little bit again. An increase in the substrate concentration while maintaining a constant enzyme concentration leads to a proportional increase in the rate of the reaction only initially. However, once most of the active sites are occupied, the reaction rate levels off regardless of further increase in substrate concentration. At high concentrations of substrate, the reaction rate approaches its maximum velocity and is no longer changed by further increase in substrate concentration. So at high concentrations, we're approaching Vmax, and the change in velocity is not affected. And so the increase in the rate of reaction is no longer proportional. All right. That's number 2. Number 3 is B. 4 is A. 5 is A. 6 is D. 7 is A. 8 is A. 9 is C. 10 is B. 11 is C, not D. Lyases are responsible for the breakdown of a single molecule into 2 molecules without the addition of water or the transfer of electrons. Lyases often form cyclic compounds or double bonds in the products to accommodate this. Water was not a reactant and no cofactor was mentioned. Thus, lyase choice C remains the best choice. Is that right? 11, I said transferase just because of ATP. But since they have 1 reactant and 2 products, they're saying it's a lyase because it doesn't use water the way hydrolase does. It's not a ligase because that's addition or synthesis. Transferase. Why couldn't it be a transferase though? 11. No cofactor was mentioned. Transferase transfer from one to another. This is just breaking ATP into 2 other molecules. So it's not so much a transferase as a lyase. All right, fine. 11, C. 12 is D. 13 is D, not C. Cooperative enzymes demonstrate a change in affinity for the substrate depending on how many substrate molecules are bound and whether the last change was accomplished because a substrate molecule was bound or left the active site of the enzyme. Because we cannot determine whether the most recent reaction was binding or dissociation, A and B are eliminated. We can make absolute comparisons though. The unbound enzyme has the lowest affinity for substrate, and the enzyme with all but one subunit bound has the highest. The increase in affinity is not linear, and therefore choice C is not necessarily true. An enzyme with two subunits occupied must have a higher affinity for the substrate than the same enzyme with only one subunit occupied. Thus, choice D is correct. The affinity is greater. We don't know if it's increasing or decreasing, but it's strictly greater. All right. The affinity is greater. We don't know if it's increasing at a greater rate or not. I guess. Is that what they're saying? Let's see. 13. An enzyme with two subunits occupied must have a higher affinity for the substrate than the same enzyme with only one subunit occupied. So if it had 3 and it went down to 2, wouldn't its affinity be lower than before, but not lower than if it was going from 1 up to 2? That's what they're saying. If you say so. 13D. 14 is A, not C. Triglycerides are unlikely to act as coenzymes for a few reasons, including their large size, natural charge, and ubiquity in cells. Cofactors and coenzymes tend to be small in size, such as metal ions like choice C, or small organic molecules. They can usually carry a charge by ionization, protonation, or deprotonation. Finally, they are usually in low, tightly regulated concentrations within cells. Metabolic pathways would be expected to include both oxidation-reduction reactions and movement of functional groups, thus eliminating choices B and D. They said it's A, not C. Magnesium acting as a cofactor So magnesium acting as a cofactor, they're saying, has to do with carrying charge, and so it is relevant to metabolic reactions, just like oxidoreductase is about moving electrons. Magnesium as a cofactor also is usually involved in that kind of thing. So they're saying that is part of metabolism. On the other end, triglycerides acting as coenzymes is unlikely. Triglycerides are large, neutral, and ubiquitous. While it is relevant to metabolism, they're not coenzymes. They're substrates. I guess I could have told you that. 15, finally, is B, not D. The rate of reaction increases with temperature because the increased kinetic energy of the reactants, but reaches a peak temperature because the enzyme denatures with the disruption of hydrogen bonds at excessively high temperatures. The absence of enzyme, this peak temperature is generally much hotter. Heating a reaction provides molecules with an increased chance of achieving the activation energy, but the enzyme catalyst would typically reduce activation energy. Keep in mind that thermodynamics and kinetics are not interchangeable, so we are not considering the impact of heat on the equilibrium position. The ideal temperature is lower with a catalyst. I said D, no conclusion can be made. The rate of reaction increases with temperature because of the increased kinetic energy of the reactants, but reaches a peak temperature because the enzyme denatures. In the absence of enzyme, this peak temperature is generally much hotter. Heating a reaction provides molecules with an increased chance of achieving the activation energy, but the enzyme catalyst would typically reduce activation energy. Keep in mind that thermodynamics and kinetics are not interchangeable, so we are not considering the impact of heat on the equilibrium position. See, the ideal temperature is lower with the catalyst because it denatures the catalyst, not because thermodynamics and kinetics are interchangeable. We're not considering the impact of heat on the equilibrium position. So once again, the ideal temperature is lower with the catalyst because it denatures at high temperatures and it just doesn't need to get that high. It can achieve the reaction rate without getting that high. All right, well, there you have it. That is chapter 2, enzymes. Next time, chapter 3, non-enzymatic protein function and protein analysis. Thanks for watching. I'll